Good morning, everyone. Good afternoon, good evening, wherever you are in the world. We're grateful to have you join us in this webinar today. Uh, we we're going to present this webinar today by Keith Chrzan's going to present getting sample size right, what they didn't teach you in school. So we're excited for that. Just a few housekeeping items before we start. There is a Q&A button at the bottom of your Zoom screen. We'd encourage you to use that button to ask questions, not the chat button. So you can go ahead and ask questions during the webinar. We have Dan Yardley here as well, and he's going to help answer some of those questions as Keith is presenting. And then we'll have a Q&A section at the end. Just to be really clear, this question comes up a lot, but after the webinar, a few business days after the webinar, we will send out a link to this recording. And in this case, we'll also send out a calculator, an Excel calculator, to help with sample size. Okay, so let's see, Keith. Okay, yeah. One last thing here. Just like to encourage you to check out our Discover product. We're really excited about it. We've been working hard. It's getting more powerful every day. Keith, can you put your mute on? I think we're getting some feedback there. Thank you. So you can check out Discover at discover.sawtoothsoftware.com. Also, Keith and Dan are part of our amazing consulting team. So if you want to partner with us on your next project, you can reach out to Keith and team at analytics@sawtoothsoftware.com. We also would like you to know that we now sell sample. So just convenient and easy to purchase sample through us. And you can reach out to our sales team, sales@sawtoothsoftware.com, to talk to them about sample. So with that, I'd like to introduce Keith Chrzan. So give a proper introduction. So since 2012, Keith Chrzan has been the SVP of Sawtooth Software's analytical consulting practice. Prior to joining Sawtooth Software, Keith spent 12 great years as Chief Research Officer at Merits Research. And before that, he was head of marketing at IntelliQuest. He's also had wonderful client-side research experiences at both Behring Mannheim Diagnostics and Bayer. Keith has a BA in philosophy of religion from Notre Dame, and he's made that marketable with adding an MBA in marketing from Indiana University in Bloomington. He's also a frequent speaker at industry conferences. Keith has co-authored 2 books on choice modeling and written over a dozen academic papers on various analytical topics. So with that, Keith, take it away.
Thanks, Justin. Okay. So today we're going to talk about sample size. And sample size is important because if you don't have enough of it, some bad stuff can happen, right? So your research may not even be credible if you didn't talk to enough people, or you might not be able to answer questions with a lot of confidence because your margins of error are wide. But of course, sample size costs money, and having larger samples sometimes takes longer in the field, and time and money are 2 pretty important things too. So we really need to size our samples properly, because we want to balance this trade-off between the bad stuff that happens from too little sample and the bad stuff that can happen from having too much. I want to warn you a little bit here. There's going to be a little bit of math, but there's really just going to be one equation. I'm going to abuse it a little bit and twist it around and change some shapes on it, but it's really just the same equation again and again and again. And I'm going to include a part that's usually missing that you might not be familiar with. So that's kind of the tricky part here. Let's get into it. Little refresher, back in Stats 101, you would have learned about hypothesis testing. We've got some null hypothesis test that we test. And as the result of our statistical test, we either reject that null hypothesis or we fail to reject it. Everything's great if we reject a hypothesis that's false, or if we fail to reject one that's true. In those two situations, we're in great shape. Otherwise, there's some errors that happen. And the one you might have remembered, one you probably most remember from your days in stats class is type 1 error. And that's the crime of rejecting a true null hypothesis. and thereby believing something that isn't true. We denote this probability with the Greek letter alpha. Alpha you'll also recognize as our significance level. It's something that we use to define confidence intervals. And because we don't want to run around making false claims, we like alpha to be really small, which is why we talk about 95% confidence intervals or statistical tests with a 5% error rate. Alpha equals 0.05. After your stats professor taught you about confidence intervals, there was a little section about sample size. And if you take this little formula here this is the formula for the width of a confidence interval. So the width of that confidence interval is a function of the z value associated with your type 1 error rate alpha. The other entities in this equation are n, your sample size, and p, your expected probability. If we're talking about a proportion, this is the formula for the width of a confidence interval of a proportion. Nothing should be too strange there. Then when your professor wanted to talk about sample size, they noted, hey, look, there's an n in there. We can just go back to our high school days and do a little bit of algebra and solve for n. And if we do that, we're going to take that same equation we just had, we're going to solve it for n, and look, now we've got a formula for sample size. If we know how wide we want our confidence interval to be, and how confident we want to be that our estimate is within that interval, this formula does the trick for us. This is the equation that's built into a lot of online sample size calculators. It's built into the sample size wheels and sliders that once upon a time research companies would give away at conferences. I don't know if they still do that or not, but it's been a while since I've been to one of those conferences where research companies give away tchotchkes like that. There's other common cases of two independent proportions, a case of a mean, two independent means, or two paired means, and we're going to have formulas for all that stuff in the appendix. I'm not going to spend your time showing you more formulas because they all have the same theme about them. So we're not going to do that. But I did want to note that they're in the appendix. So let's talk about a couple of case studies here. Okay, so the first case study is we work for a research firm, and we've been asked to learn what proportion of voters in Yoknapatawpha County, Mississippi, favor the incumbent over his challenger. We'd like to be 95% confident that we estimate this percentage within plus or minus 3 percentage points of the truth. So now we've got all the information we need. We don't really know what proportion of people prefers, the mayor to the challenger. So we just put in a 0.5 there, and 1 minus, if you look at that equation, 1 minus that proportion is again 0.5. If we want to be 95% confident, you probably remember from your stats class that's measured by a z value of 1.96. And if we want our confidence interval, width to be 0.03, we put that there in the denominator, we square things, we do the math appropriately, and it tells us that we want 1,067.1 respondents. Well, we round that up to the next whole person because we can't interview a tenth of a person, and we got a sample size of 1,068. So next year, when you start seeing all the political polls out there and they talk about their samples being plus or minus 3%, this is why, because they did this formula. Hopefully that's clear enough. That should just be a bit of review. So let's go on to another case study here. Here's an advertising case study, and it's a disguised case study of something I actually worked on once upon a time. We'll say our brand has $500 million in annual sales. And with our current advertising campaign, our ad awareness is 50%. We know from past research that every 5-point increase in awareness leads to a 1-point increase in sales and therefore revenues. Management's decided to test a new ad campaign to see if it can generate a 10% bump in awareness, and they want to be 95% confident about that. So they diligently use the sample size formula we just showed. They plug in the appropriate numbers, and they end up with a sample size of 96.04. So they round that up to 97. They field an ad test, and they found that 57 of the respondents, that's 58.76%, were aware of the ad. Now they take that information and plug it into a statistical test, right, to see if that 58.76 is significantly greater than 50%. It's not. It only has a z value of 1.75, and so they stay with the current ad campaign, right? Because they rejected the hypothesis that the current ad is better than the new ad is better than the current ad. Unfortunately, it turned out that the new ad really was able to generate 60% awareness. So down here, I've got a little normal curve that shows the sampling distribution for means around for proportions. When the true proportion is 0.6, if we sampled again and again and again different samples of size 97, some would end up at 53% and some would end up at 62%, and they would follow this normal curve here. And what we can see is I've plotted the 0.5876 that we actually found. We got a little bit unlucky. But notice that if the truth is that if the real truth is that the new ad generated 60% recall, fully half the samples we'll collect will come in at under 60%. And it turns out that mistake cost the company $10 million because they went with the existing ad instead of going with the newer and better ad. We had someone take a photograph of the VP of marketing when he learned this information, and it looked like this, okay? This is the look on your face when you made a bad decision about sample size. Well, what did we do wrong, right? Why did we make this mistake? We followed the sample size formula. What could we have done differently? And at this point, I'll take responsibility, okay? I used to teach statistics at Indiana University. And when I first started teaching, power analysis, which is what we're going to talk about for the rest of today, was just an appendix at the end of the stats testing chapter. And because I was a novice professor, I skipped that appendix because it was just too darn confusing to teach my students. And I think most professors skip that section, or they cover it very quickly. And on behalf of all the other stats professors who've made the same mistake I did, I apologize. Because as marketing researchers, we really, really need to know about power. And it turns out that had we adequately accounted for power, we would very likely have saved my employer, the advertising client, $10 million. So my way of atoning for this is I'm going to walk you through the following slides, and we're going to talk about power. I should note that after I was a novice professor and I figured out that I ought to teach my students about power, I came across Sam Katchigan's stats test. It's an intro stats text, and it has simply the best section on power analysis I've ever seen. And so I'm largely going to rip off what I learned from Sam Katchigan's stats test to share with you now. Turns out, when you think about sample size, when you're going to be doing stat testing, you need to think about the other kind of error. So we talked about type 1 error, but type 2 error is failing to reject a null hypothesis. The probability of this error is denoted by beta. The complement, 1 minus beta, measures something we call power. And power is the ability to find a difference if it's really there. It's okay if you don't remember about power analysis from when you learned about confidence intervals, because power really doesn't play any role in estimating confidence intervals. And that's why it wasn't included in the sample size formula that you used. But we do need to think about power analysis when we're doing hypothesis tests, and we do need to take account of beta. So let's talk about power. Power, there's a good image for you. Power, that's what we want in our statistical tests. If something's significant, we want to be able to say so. And if it's not, of course, because we want to worry about type 1 error, we want not to say so. But this is all about saying so when it's true. Turns out it's a pretty easy thing to fix. If you didn't have Sam Katchigan's textbook, you could just ask ChatGPT how to incorporate sample size into your power calculations, and it would give you that first formula there. That looks a lot different than anything we've ever talked about. But if you go through and do some substitutions and do a little bit of algebra, it turns out that you get the formula down at the bottom there. Again, we're computing sample size as a function of p and 1 minus p. How accurate we want to be, that little d down there. Our type 1 error rate, which is measured by z of alpha over 2. And importantly, our type 2 error rate. The z statistic that's associated with beta. That's the z statistic that's associated with our desired level of power. Now, if you compare the two equations I gave you, the one earlier for computing sample size for a confidence interval and the one below computing sample size for statistical power for stat testing, the only difference is that we've added a plus z beta in there. So if you're comfortable using the first formula, you should be just as comfortable using the second formula. What level of power should we use? Well, if we ignore power altogether, like we did in estimating our confidence interval, we're implicitly assuming that z beta is 0. That gives us 50% power. That gives us only a 50% chance of finding a successful advertising campaign, even if it really would be successful. That's not a very high percentage. That's what happened that cost us $10 million in the advertising case study. If a false negative can be harmful, like in the ad test, you want to have more power. And the two levels I usually see people use are 80% power, which makes for a z beta of 0.84, or a 70% level of power, a z of 0.525. So let's go back and rethink that advertising test. Now we're going to use the right formula, the one that has z beta in it. If we're going to test at 80% power, that z beta is 0.84. And when we do our little formula there, we end up with a sample size of 196. With a sample size of 196, there's an 80% chance that we'd have a statistically significant result if, in fact, awareness for the new ad really was 60% instead of 50%. So if we really would get a 10% bump, we now have an 80% chance of finding it, whereas before we only had a 50% chance of finding it. You'll notice this formula gave us a sample size of about double what the previous formula did. So if you don't want to do math or even look at the calculator Dan's going to show you in a few minutes, and you just wanted to think about an easy rule of thumb, maybe think of it this way. Unless you've already taken power into account, if hypothesis tests are really important to you, maybe double your sample size. That's my quick and dirty, easy rule of thumb. I wouldn't advise that. I'd advise you use the calculators or the formula. But if you don't, double your sample size and you'll probably be pretty safe, at least at an 80% chance of power. A little bit more about that. Typically we test with 95% confidence, and I usually like 80% power. That means that the chance of a false positive is 5%. That's 100% minus the 95% confidence. The chance of a false negative is 20%. That's 100% minus the 80% power. But I ask myself, is it really true that a false positive is 4 times as harmful as a false negative? In stats class, they really, it was a professor teaching, and there's an academic bias about not making false claims. And so there's a hesitancy, to make false claims. And so they make the confidence level really high, like 95%. But my advice is, if it's possible, think about the business cost of the two errors and try to make your chances of error proportional to those costs. Let me give you an example. If we go back to the advertising test, turns out the cost of producing the ad was $3.33 million. We've already said that the potential loss of sales was $10 million. That means that a false negative is 3 times as harmful to the business as a false positive would be. And so my suggestion is, let's maybe calibrate our errors to keep that proportion in mind. Let's maybe test with 85% confidence and 95% power. And if we plug those numbers in there and work the math, we find that we need a sample size of 229. I just think it's a little bit naive to always do all of our stats tests at 95% confidence and implicitly at only 50% power. I think we ought to think about it. And if we do, we almost always want more power than we usually have. And we might think further about quantifying the harm to our company of a type 1 error and a type 2 error, of a false positive and a false negative. And now we have the mathematical tools that allow us to do that. So like I said, that was a basic review of sample size for a single proportion when we want to think about having a confidence interval versus when we want to think about doing stat tests. I also mentioned that Dan's going to provide a little calculator that's going to allow you to do that calculation for both confidence intervals and stat tests for the cases of one proportion, two independent proportions, a single mean, two independent means, and two paired means. All 5 of the common situations that you probably remember learning about in Stats 101. We've got an Excel calculator we're going to give you that Dan's going to demo for you. And we also have all of those equations, all 10 of those equations, in the appendix to this presentation. Before we get there, though, I know that people, they often, another way that sample size comes up from my clients, at least, my clients always want to know what kind of sample do we need to do this kind of analysis or that kind of analysis. And so let's talk about some sample size recommendations for complex studies. For segmentation studies, there have been a series of analyses done of what kind of sample size you should have. There's a really good book on segmentation by Dolnikar et al. And their recommendation, based on all of these studies that have been done, and even a couple of studies that they did, was that you should probably have 100 times as many respondents as you have basis variables in your segmentation. So if you're going to run your segmentation and you've got 25 basis variables that you want to use to create your segments, you might want to think about having a sample size of 2,500. Another way to think about segmentation is to think ahead a little bit and realize that you're going to want enough set respondents in each of your segments to allow you to have powerful enough statistical tests to be able to detect differences so that you can profile your segments. And so you might want to think, hey, boy, if I, really I'm likely to have somewhere between 3 and 6 segments. No client ever wants to pay for fewer than 3 in my experience. And most clients have a real hard time dealing with more than 5 or 6 segments. So if I wanted to have, worst case, maybe I've got 6 segments. If I wanted to have on average 200 or 300 respondents, maybe I want 1,200 to 1,800 respondents in my segmentation study. So we've got a couple different ways of thinking about it. You can think about how many respondents per segment you want to make, to do segment profiling. Or you can also just think, boy, I'd really like to have 100 times as many respondents as I have basis variables. Okay. Another area that I get questions is driver analysis. And here the traditional recommendation for linear regression models is we'd like to have 10 times as many respondents, as we have potential drivers, or K. K is the number of predictors in our model. When I went back and reviewed the literature, that was a recommendation for statistically well-behaved data. But we all know how messy survey research data is, how much collinearity there is in it, how much ill conditioning is in it. And in that case, we should probably shoot for a larger sample size. So I really recommend that we have 20 times as many observations as we have variables in our model, just to account for the fact that I know in advance how messy survey data is. If we're running a logistic regression or a binary logit model, there's a different formula I've seen. You want to have 10 times the number of parameters in your model, the number of predictor variables in your model, that's K, divided by P, where P is the proportion of the less chosen alternative. So if we're trying to model whether people like our brand or not, and we have some advanced information that we think about 2/3 of the people like it, P would be about a third, or 0.35 in this example. And we would just plug the numbers in there, and we'd have our sample size estimate. Not a lot of, for good reasons, a lot of practitioners don't do factor analysis anymore, but it is something I end up doing once or twice a year. And when we're going to do factor analysis, historically, the advice was that if you have a sample size of less than 100, that's pretty poor. 200 is about fair, and 300 is a good sample size. But again, given the messiness that we have, of survey data, I still think it's best to err on the high side. And so I would usually shoot for a sample of at least 300 or 400 respondents if I really wanted to have a very reliable factor analysis. We do a lot of data mining with things like classification and regression trees. I don't know if you do a lot of this or not, but if you know about trees, what happens is you start off with your whole sample. The tree splits the sample into two, not necessarily even pieces, and then each of those pieces gets subsequently split again and again and again, as long as splitting is significant. And so what happens, each split, your sample size gets cut in half. And so you very quickly, if you want a very rich tree at all, you want to have enough sample that allows it to split enough times. If you start off with a small sample, you're going to end up with a nasty little shrub that doesn't look very healthy, and your client's not going to be very impressed with the tree that you build. So I think it's usually good to start off with a sample size of 1,000 or more if you're going to run a classification tree or a regression tree. A lot of times, though, I'm not just running trees so that I can have a nice visualization of my model. I'm really just I want to run an importance analysis. And in that case, I'm probably running random forests, which are going to be hundreds or thousands of trees I'm going to be running. And in that case, I'm willing to go lower on my sample size if I'm measuring importance, because I'm relying on the forest to decorrelate my variables for me. So I'm usually comfortable going much smaller with a random forest. If you're going to be doing a max diff analysis, you might see we have an appendix in our book, Becoming an Expert in Conjoint Analysis, that talks about a quick and easy way of doing power analysis for choice experiments. So I would encourage you to look at that book. It's something very easy to do in Lighthouse Studio, our software for doing choice modeling. There's some native capabilities built inside of Lighthouse Studio for testing our designs. And it turns out you can use those to do power analysis as well, which is kind of cool. For a conjoint study, again, I'd refer to that appendix. But a second way of thinking about it, just like in segmentation, we had a couple different ways of thinking about it. Another way we might want to think about sample size for conjoint is to think about our ultimate deliverable, which is usually going to be a simulator. How precise do we want the share estimates from our simulator to be? And what size differences do we want to be able to call significant? So maybe if we're going to answer the first question, we might want to use the formula that I provided earlier for the confidence interval around a proportion. And if we want to think about differences or stat testing, we might want to think about the sample size for differences in proportion, which will be built into Dan's calculator. By way of summary, there's some simple formulas that exist to calculate sample size. In school, we learned about one of those formulas when we wanted to do confidence intervals. But really, as professional marketing researchers, we kind of need to know about both of them, whether we're doing confidence intervals or hypothesis testing. Make sure you use the right formula for your needs, because we want the image on the left there, power, and not the distressed VP of marketing there on the right who lost $10 million. That's not the person we want to be. I've got some references here. The Sam Katchigan book I talked about. The other references that I use to get references on sample size for more complex kinds of studies. I've got a reference to a web-based sample size calculator down there at the bottom. Most of the online calculators only estimate sample size for confidence intervals, but if you want to do for both confidence intervals and power, I would encourage you to go to that calculator. That's the one to use. Most of the rest you should ignore for good reason. And the reason is, though, those calculators just estimate sample size for confidence intervals, not for power. There's two here that we looked at recently, one at Conjointly, one at Qualtrics.com. Both of them are particularly impoverished because, again, not only do they just work for confidence intervals, they only work for the case of a single proportion, which is, they stop like halfway through Stats 101 or less, and they're really not giving you all what you need. I go to that one at the University of British Columbia. That's a good one. Or you can use the formulas that are in this document and its appendix, or you can use the Sawtooth Software sample size calculator that we've built into an Excel workbook. Actually, my colleague Dan Yardley built that workbook, and he's going to walk you through a demonstration now.
Hey, Keith, maybe we can answer a few of these questions, not all of them, but a few of them before the demo, and then
certainly
the rest of them after the demo. Keith, if you could bring up the Q&A button, the bottom of your screen, we can just start at the top with Derek Miller's question.
Okay, sample size calc, they can get pretty complicated. Yeah, if you're doing something really complicated, like the max diff or the conjoint experiment, you can actually use the simulator that's built, or you can actually use the we've got a simulator essentially built into our sample size tool or our design testing tool in Lighthouse Studio. So that's a case where I would definitely use a simulation rather than the formula. The formulas for estimating the power of a conjoint experiment are pretty convoluted. I know there's an R program that'll do it for you, but it requires a lot of inputs. And I think just using the design test functionality in Sawtooth Software in our Lighthouse Studio is an easier way to do that. Thanks, Frank. I'm glad you thought so. Okay, Santiago. This is a good question too. You're right. Everything I've done assumes that we've done, probability sampling and not non-probability sampling. I don't even know. I have to tell you, I'm not an expert on non-probability sampling. I guess I'm kind of old-fashioned, and I view non-probability sampling as being not a lot different than junk. And so I don't know that having more junk is necessarily better than having a lot less junk, unless you do something to solve the junkiness of it. And I know that if you're dealing with non-probability samples, there are things like propensity weighting and some other tools that you can use to make those samples more and a method called matching that you can use to make those samples more representative. But how that interacts with sample size calculations, I have to say I don't know. Okay, we talked about the number of variables. Norman asks, what about when we have units within each variable, like levels of age group or 100 different locations? In that case, I would say that those sample size calculations apply in each age group or in each different location. If I have to think about what the level of reporting I'm going to be doing. If I'm doing location-specific reporting, I need to think about what's the width of the confidence interval I need to get to be, that I'm shooting for the accuracy at each location. Likewise, if I'm doing a stat test and comparing location A and B, I want to have enough power to make that calculation. So I think you have to do that calculation, at the level that you're going to be reporting at, and not at the total sample level.
Okay, Keith, maybe just one more, and then
sure.
We'll let Dan.
Yeah, Tom asks if the size of the smallest sample should we consider the size of the smallest sample? And Tom, that's a great suggestion. If we have reason to believe or suspect or fear that one of our samples might be, one of our segments might be really, really small, we might have to either oversample to get that segment, or just collect a larger sample to begin with, so that our small segment ends up not being too small. I recently did a segmentation study like that, where we knew in advance that one of the segments was only going to be like 3 or 4 or 5% of the population, and we oversampled for that. So yeah, that's a good question. Thank you. But Justin says we're going to move on now, so we'll have Dan take it
Yeah.
away.
Yeah, we'll get to the rest of the questions after Dan's demo.
Okay, great. Yeah, thanks, Keith. This is fantastic stuff. Let me go ahead and share my screen here with the little Excel tool that I put together. Should be able to see my screen now. Yeah, so here is the key, some of the Keith's examples that he had in his presentation. The layout is similar for each of these tabs. We have single proportions, single mean, paired means, and independent proportions. We have formulas to calculate all of these sample size for precision and sample size for power. This top one here is does not take into account power. And this the way you would do this one for power is you'd put in like your best guess proportions. Here we were thinking that 50-50. Here's our confidence interval of 95%. And then we put in our power level of 80%. And this that size, that difference that we want to detect. Here we wanted to take that 0.1. And then down here it spits out this projected sample size that's needed. And again, if you put in the 50% for power, that gives us back to the same equation as the sample size of precision. So if we change this difference there the same, you can see that those are the same because it basically takes that power out of the equation by making that beta z 0. So we'll put that back to the 80%. So that's how this works in a nutshell. Also, we have listed out all the formulas that we used that are being done underneath the hood for you. And yeah, so that's it. And I'll turn the time back over to Keith to answer some more of these great questions that we have. Oh, you're still on mute, Keith.
Thank you. I'm working on sharing my screen again here. So we got some more questions came in.
Yeah, before we do that, Keith, could you advance the slides there? Just one more housekeeping thing. We will send out the slides. We'll send out the recording to everyone who attended and who registered. That will get to you in a few business days. And we're also going to send you a link to that calculator that Dan showed. So everyone will be getting that. Just a reminder, check out Discover. We're making an awesome product there. It's going to get better and better. And Keith and Dan are super friendly and super smart and experienced. I'd recommend you consider them to help you out on your next project. And yeah, we do sell sample, which is helping you recruit people to take your surveys. We work with various providers to do that. Wow, there's so many. By the way, thank you, Keith, for such a great presentation, and Dan. There's a lot of questions here, more than I've seen in a long time. So just a lot of interest in this subject. Keith, if you want to advance the slide, and then Keith and Dan, you guys can turn on your cameras, and we can keep answering all of these questions until we're done.
Okay.
One more thing, Keith. If you could read the question, our attendees can't see the questions.
Okay.
So if you could read the question and then answer, that would be great.
Okay. David Hangehold asks, what are your go-to driver analysis techniques given multicollinearity of the predictors? We did a webinar a while back called Driver Analysis, How to Do It Badly and Well, and I think that's up on our website. So you can see what our recommendations are there, which are mostly, we like averaging over orderings if we've got 20 predictor variables or less. We like Johnson's relative importance weights if we've got more than 20 predictors. And I usually use random forest if I have a mix of metric and categorical predictors. So those are the three methods that I use. Mikhail asks, do we have any books or tutorials or recommendations for sample size calculation for Bayesian inference? Unfortunately, I do not. I'm sorry. That's not a reference I have handy. I should probably actually check my Bayesian statistics books here and see if I could maybe add to this presentation for next time. So thank you. That's part of the continuing process of quality improvement. We'll try to get that improved. Oliver asks, in Lighthouse Studio, you can simulate the errors for CBC. The documentation says we'd like errors of less than 0.05 for main effects, and less than 0.1 for interactions. Where do those come from, and do I have a reference? Those basically just come from some years and years and years of practical experience and what works well. And I don't have any recommendation other than that's just, I don't have any reference other than that's a recommendation we've been making for years based on prior experience. Rebecca says most formulas for sample size in SAS and R include both alpha and 1 minus beta power. And that's right. I talked about one of the sample size formulas that I use for choice experiments in R. I haven't used SAS in like 25 years now, but I trust that that's true. I'm not a SAS user, so I don't know. How can we use these ideas to measure the total size of a market? Well, I would say that if you want to measure it within plus or minus, 10% accuracy, go out and sample, use these formulas, and they'll tell you to go out and sample, 400 or 100 people. If you want to estimate the size of your market within plus or minus 5%, get yourself a good probability sample, like a random sample, and estimate to plus or minus 5% when you have a sample size of 400. Okay. Do you think you could build a power calculator? Yes. Several people have. The university that I recommended has a nice one on their website, and Dan built an Excel one for you. How do we deal with a small sample population, Robert asks. For example, 200 neurosurgeons. How do we determine a sample size that would be statistically significant? Because we can't test everyone after all. That's true, we can't get everyone. And the formulas I've given and that Dan has built into the calculator all assume that we have what statisticians would call an infinite sample. When you have a finite sample, there's a modification you make to those formulas. You built in something called the finite sample, the finite population correction factor, the FPC. We didn't do that in ours because it really, beyond the very simple cases, it makes the math very, very difficult. And in my career, I've only come across this 2 or 3 times where I've had to use the finite population correction factor. So it's just not that common of a thing. And I do a lot of pharmaceutical work. And the reason is you're only really going to run into the finite population correction factor. You're only going to really need to use it when you're interviewing more than 5% of the population. So if you had a total population, maybe if you were talking about neurologists in Portugal, then you have a finite population and you'd want to include that finite population correction factor in your calculations. But otherwise, even if you're doing something like that political survey in Yoknapatawpha County, Mississippi, even Yoknapatawpha County has enough people in it that it's very unlikely you're going to be sampling more than 5% of the population. So if the population was, 100,000 people in the county, then, you're really probably not going to be surveying 5,000 people or more. So I think that population correction factor just doesn't come up very often. Someone who's anonymous asked about the decision analyst mobile stats calculator, which, by the way, I have on my phone. That's kind of nice because it does take into account the finite population correction factor that I just talked about, but it only does it for confidence intervals. I don't think they handle the case of power, which, if you can't tell anything else from this presentation, I think people don't pay enough attention to power. Okay. Another anonymous attendee asked, is there a concern with having too much power or too much power, too much sample? There's something you could think about the effect size or what the minimum effect you'd want to be able to measure is, and not have too much sample, right? Because I know I used to do work in the automotive industry quite a bit, and we did some tracking studies, and routinely we had sample sizes of over 100,000 respondents. And, we were basically surveying everybody who bought a car in the month, things like that. And so we had very high numbers. And if we did stat tests, it turns out everything is significant. And so rather than pay attention to stat tests and where every single difference, no matter how small, is significant, we would have to think about what's the size of difference that makes marketing sense. And then look for those differences rather than the ones that were statistically significant because the statistical tests had too much power. Yeah, we talked about, when we've got methods beyond simple random sampling or stratified or cluster sampling, the more complex your sampling plan is, and especially if it's non-probability sampling, these formulas aren't going to be the ones to use. You're going to have to use different ones and use the right formulas. Oliver asks, in chapter 7 of the Applied Max Diff book, we walk through some sample size calculations that refer to the margin of error. The margin of error in that particular chapter was based on an academic paper that came out in the Journal of Choice Modeling. They came up with their own way of estimating utilities from counts, and then thinking about the margin of error for that particular way of estimating. So that chapter is very, very specific. Can we provide a link to the references for the max diff sample size calculation? That would be in the Applied Max Diff book. If you want to write me an email after this presentation's over, I'll be glad to send you a reference to that article that was there. Let's see. Is there a discount for subscriptions to Lighthouse Studio for students? I think there is, but I'm not allowed to sell. I'm not in the software sales side of the business, and I don't answer those questions. I don't even know the answer to those questions. So I would contact sales@sawtoothsoftware.com, I think would be, or support@sawtoothsoftware.com. Those would be the best ways to get that information. Let's see what else we've got. Oh, Victor asks, regarding weighting and its effect on effective sample size, is there any guideline on how much to oversample when weighting is expected? I just wrote a white paper that we're going to put up on our knowledge base about weighting and about the effective sample size. And so the answer is yes, there are samples, there are formulas for doing that. And maybe that would be a really good thing to add to a future webinar. That's really that's a good suggestion. We'll have to think about adding a weighting presentation. I think that would be valuable. Audrey asks, have I tried G-Power? It's free software that calculates power. Audrey, I tried that last month. I tried a couple times. I had a real hard time getting it installed, and then I had some client projects come up, and I haven't been able to get back to it. But my belief from reading the directions is that G-Power would do a lot of what the sample size calculator that Dan's going to be providing is. I think it takes into account both confidence levels and power. Mikhail asked about survey weighting, and so I said, yeah, that's a good question for another day. Eric just said finite population correction factor. I don't know if there's like an explanation point after that or something, but it is something we need to worry about when we have teeny tiny samples. Maybe that would be something we could add on another day as well. Okay. How do we Tom Eagle asks, how do we calculate multinomial logit sample size if the above is true? I'm not sure. Oh, his above question. Multinomial logit model, should the errors be calculated using Monte Carlo because the probabilities are multinomially distributed? I have to admit, Tom, I like the idea of using Monte Carlo simulations when we're in complicated situations that aren't easy to handle with formulas. So I would say yes, but my guess is the next time we're live, I'm going to ask you to tell me what the answer is, because I suspect you know better than I do. I think with that note, I think we've reached the end.
Keith, can you just double check there's anything else there?
Let's see. Jeffrey Clark asked if we can bring up Lighthouse Studio and check and show where the sample size power calculations are performed. Okay, the power calculations aren't. That's described in the appendix that I talked about in the Becoming an Expert in Conjoint Analysis book. But I can, if we have time, Justin, do you want me to load up Lighthouse Studio and show that?
I'm not sure. Is there anything else there that we haven't answered?
Oh, here we go. Eric Levy asked, once we've established the cost of a mistake and success, should the organization use this information going forward to improve their decision making? And I think my answer there is a resounding yes. I think that's what I was trying to show with the advertising case study is, if you know what the costs of a mistake, in that case, yeah, if you knew the cost of a mistake and of both mistakes, a type 1 and a type 2 error, I really think we should adjust our sample size according to avoiding both of those errors in the correct proportion. Even if we don't know what the costs are, we should probably realize that when we're doing stat testing, we want to be stat testing with more than 50% power. We want more than a 50% chance of finding a difference if there's really one there. And so even if you don't know what those costs are, you should at least think to yourself, yeah, there's probably a pretty substantial cost to answering no when the correct answer is yes, and taking power into account.
Yeah, so Dan, maybe you can bring up the Lighthouse Studio screen there while Keith continues to answer some of these other questions, and then it will be nice and seamless.
Okay.
Keith, do you see anything else?
I I do not. I think we covered all the questions there, if I'm not mistaken. Oh, wait, someone asked, an anonymous attendee asked, curious is about the sources of sample you sell, given concerns regarding non-probability samples. So, and the answer is, I'm not the guy, I haven't been involved in selling samples, so I don't know the answer to that. Do you, Justin?
Yeah, we work with various panel providers, sample providers. So we can help you out. You just give us a call, give us an email, and we can work through that.
Okay, I don't. There we go.
Okay, I'm showing Lighthouse Studio here, and I've loaded in our sample CBC study. What was the question again, and where do I go, Keith? Find the sample size.
Okay, go to, you've got a golf exercise there. Go to that exercise.
Okay.
Click on one of the CBC questions. Go to the Design tab. And now we're going to, let's go hit the, so we created a design already that has 12 tasks, some number of versions, 3 concepts per task using the balanced overlap strategy. So go to test design. We're going to do the advanced test. And let's say that we think our sample size might be 200 respondents. Let's change that respondents to 200, run the test. And what it's doing is so now okay, go to the standard errors tab there at the bottom. And now it's giving us the size of our standard errors for each of our parameters, each of our sets of utilities. This is using an aggregate logit model. So now it looks like our standard errors are all in the 0.4, 0.3 range. If we wanted to, let's do a what if now. Let's close that. And now our client comes back and said, let's do the test again. Test design, except now the client says, I can't get 100 respondents. What about 50? Could we get by with 50? So put 50 in there and let's test it again and look at our standard errors. And now we can see, well, our standard errors have gotten a lot bigger. What they've done is they've pretty much exactly doubled, right? Because of the math of standard errors and sample size. They've doubled from the 0.3, 0.4 range to the 0.6, 0.7, 0.8 range. And so we'd have to ask ourselves, is that accurate enough to answer the kind of questions we're going to have or not? I know that with a sample size of, just of 50, if we're going to run 2 simulations and compare them, a lot of times we're not going to get a significant difference, even when the differences are pretty large. So that's something to think about. And that thing I just did in my head of, think about differences between 2 simulations. That's the situation for the stat test and the power analysis that we talk about in that appendix to the sample size chapter in the Becoming an Expert in Conjoint Analysis book. Okay, let's see.
Keith, there's a few more. Nora at the end there, 1050.
Yeah, so Lighthouse Studio uses the hierarchical Bayes model. Can the calculator be applied to that type of model as well? The answer is yes, you can apply it to that kind of model when you're thinking about the simulation shares. The simulator shares would work with those formulas just fine. The formulas for the coefficients of the model itself, though, you really need to use. You need to do a simulation like the one Dan has on the screen there. Let's see. I thought we had another. How confidently can we use the rule of thumb for determining conjoint samples? There's a formula in our book that for conjoint analysis. It's one of several formulas we talk about in the book. We found that formula works really well, and so that's why we put it in the book. It seems like a good, if you want a good rule of thumb without doing a whole lot of calculating, that's not a bad place to start.
Okay, that's it. Thanks, Keith. Great job, Keith and Dan, and so many questions, and we appreciate everybody. Hope everybody has a great holiday season, and we'll see you next time. Thanks, guys. Bye.